Hello, today we're going to explore solving quadratic functions that are in vertex form, solving equations related to those functions, and we're going to use graphical approach to support our geometric or algebraic approach. So we start by making a prediction of what the solutions to the left side and to the right hand side will look like. The right hand side is y equals 10, so that's just a horizontal line where y is always 10. On the left hand side, the y is always changed depending on x, and it produces a parabola. So I can tell by examination when I put 0 in for x that the y-intercept for the left-hand side is going to be 18, which is above 10, and or sorry, 20, which is above 10. So I know that my intersections are going to be both on the right-hand side positive. To make a more detailed graph then, now that I know what I'm anticipating, I start off by finding where the vertex is located, identifying our a value, which tells me to go over 1 up 2 instead of over 1 up 1. We're also going to go over 2 up 8 instead of going over 2 up 4. And that actually shows me the intersections, because when I have to take my vertex and I go over 2 up 8, I hit the line y equals 10 because I'm already 2 up. So I know my solutions are x equals 1 and x equals 5, and I realize how much easier it was to do this geometrically than it was to have to do any algebra. But since it's an algebra class, let's learn how to do it algebraically, find solutions to the equation. Essentially what we're going to do is we're going to peel away the layers of all the things that have been done to x so that we can just get down to the root x itself. Once I put a number in for x, the first thing I have to do is subtract 3, then I have to square, then I double, and then I add 2. If we want to get down to the root of x, then we have to undo all the other stuff in reverse order. So if the last thing I did was add 2, then I'm going to inverse add 2, which is subtract 2 from both sides of the equation. The second to last thing I did was multiply 2, so I'm going to inverse multiply 2, which is divide 2, and that gives me x minus 3 squared equals 4. Now the second to last thing I did was square, so I'm going to inverse square, take the square root of both sides. And that, again, remember, when we square root a squared variable, we have to include the absolute value to account for the negativity that could have been inside and was negated. And when we have absolute values, there's two different scenarios. One where we have a decreasing line and the other where we have an increasing line, so we account for both. And then here I'm just going to multiply the negative over to the other side, and then produces a plus or minus style equation. Add 3 to both sides and we get x equals 1 or 5, which is no surprise. But what it does do is it confirms that this is a valid way of algebraically solving what I've already solved graphically. And if there's any doubt, you can substitute one of the values or both into the equation if you have the time. Realize that this method works no matter how intimidating looking the equations can be. Even though these are all fractions, we can still follow the exact same procedures. So we start by shifting to the left 1/2 and down 3/4. Notice I know where the y-intercept is by inspection. I took a half squared, which is 1/4, take away 3/4, we're going to be at negative 1/2 right here. So that gives me information as to where the parabola is going to intersect the horizontal line at 5.5. Make a more detailed graph, and that's what you get. Notice that even though I'm working with fractions, I went over a half, so here's over a half, down 3/4, and from that point I can go over 1, up 1, and I can actually figure out where my key points are going to be located. I was intimidated by the fractions, so I just extrapolated my parabola, and I'm going to hope for the best. So this is more where the graph is used as an estimating tool. I still will have a positive solution, which will be smaller than my negative solution in terms of absolute value, and that's what I get from the graph. So back to the algebraic approach, I'm going to invert subtract 3/4, which is add 3/4 to both sides. And I wrote 11 as 22/4, so that gives us 25/4 on the right hand side, which happens to be a perfect square. So now when I inverse the square, I get the absolute value of x plus a half, and then I get the square root of 25/4, which 5/2 times 5/2 equals 25/4, so I know the square root. And then we split up the absolute value into 2, and then we regroup after we multiply one side by the negative, both sides by the negative. And we end up with negative 1/2 plus 5/2, negative 1/2 minus 5/2, which gives us 2 or negative 3. If I look at my graph in a little bit more detail, I'll find that that is consistent. Even if, when we're solving, we don't get perfect squares to square root, that doesn't change the procedure. So once again, we get our angry cloud. Tells me I'm going to have 2 positive solutions, and with more details, I can estimate that one of the solutions is going to be between 1 and 2, and the other one is going to be between 6 and 7. And I still take the square root of both sides, but you'll notice what I did here is I don't know the square root of 5, so I just leave it as the square root of 5. And then when I multiply both sides by a negative or a positive one, I end up with plus or minus the square root of 5. And so this is the exact form of my solutions, 4 plus or minus the square root of 5. But it's worthwhile to make sure that you did all the work correctly to estimate the values and see that they're consistent with what I should see on the graph. So if I understand that the square root of 5 is really just a smidge more than 2, because 2 times 2 equals 4, then we're just going to start with our axis of symmetry 4 and move above 2 and then a little bit of change, and then we're going to move below 2 plus a little bit of change. So when we look at our graph, we can see from 4 we go 1, 2, 6 and a little bit of change, and then we go back to, so we're not 2, less a little bit more change, so we're between 1 and 2. And that's how I can estimate and make sure that my graph and my algebra are in agreement. Alright, one last bit of information, and by the way, sorry for all the sniffles. It is what it is. So, when we were studying absolute values, we learned that to determine the a value, what we had to do was, if we have a number multiplied by x affecting the slope of the line, we needed to factor that out so we can figure out our horizontal shift properly. So we factor out the 2, and then we observe that you could take the absolute value of the 2 and the x plus 3 separately. And since the absolute value of 2 is just 2, we can write it like this. So the absolute value of 2x plus 6 is actually 2 times the absolute value of x plus 3. These are equivalent expressions. Well, here we have 3x minus 4 quantity squared equals 8. We're going to do something similar, but it's got to be modified because of the fact that we're squaring. So in the first case, you can see I just took out the 3 from both the 3x and the 4, which is why I get 3 times the quantity x minus 4 thirds, all squared, equals 8. Now I just want to see what happens when you square a product, because if I take 3 times 4 squared, I know that 3 times 4 is 12, so this is 12 squared, which is 144. And my question is, would that be the same as if I took 3 squared times 4 squared? In other words, can I distribute the square into the product? If it's a product squared, is that equal to the is the square of a product equal to the product of the squares? Let's find out. 3 squared is 9, 4 squared is 16, 9 times 16 equals 144. So this gave me the same result. In the one case, multiply first and then square, or in the other case, square first and then multiply, get the same results. This should make sense because 3 times 4 squared is 3 times 4 times 3 times 4. Which, if you looked at it, it's really 3 times 3 times 4 times 4. So we can square them individually and get the same results. That then enables me to follow this logic, that if we have 3 times something squared, we can make it 3 squared times something squared and still be valid, which now produces an a value of 9. So 3x minus 4 is misleading in terms of the transformations. It's easier to see this way, that with the parabola is shifted to the right 1 1/3, not 4, and that the stretch vertically is a 9 times factor stretch, not a 3 times factor stretch. So we can now have our a value and our h value all sorted out, which enables us to follow the same procedures for graphing. Notice I start with my vertex over 1 1/3, and then I simply move over 1 up 9, and then back 1 up 9. And there we can see, since y equals 8 was the line that we're interested in, we can see the parabola already crosses by the time we go 1 to the left and to the right of the axis of symmetry. Now for the algebra, take the square root of both sides, include the absolute value, break up into 2 separate equations, regroup with a plus or a minus, and solve. And since I know that the square root of 8/9 is only about 1, it's just actually a little smaller than 1, I can ascertain that my solutions are in fact correct, because we want to be just short of 1 before we get to 9 there. So, hope this is helpful. Have a great day.